Yes, can you hear me now? How's that? Hey, good afternoon, everybody. I'm not starting yet. I know I've still got a few minutes. Folks are still coming in. I hope you like my funny clips. And obviously, Alan Turing, 100 years this year. I thought it was quite an interesting kind of start to it. Wow, this is amazing. Last session of the day. I didn't think I would get this many people. So thank you so much for coming along, by the way. I really do appreciate it. Everybody enjoying TechEd, by the way? Who's here for the first time? Any TechEd virgins? I'll take special care of you. Okay, you know, well, we got 5 minutes, right? You look like a nice, friendly kind of audience. I'll tell you, I was in the US a couple of weeks ago. Oh, they were ugly. I'm telling you, they were so ugly. You guys are much prettier. I'm telling you. It's an absolute fact. I'm doing a session tomorrow on bring your own device. So security about bring your own device. And it's quite interesting, actually, because I've got a funny story to tell you. Anybody got an iPad? I can say it because we're not recording yet. Okay? Who's got an iPad, yeah? Well, last year, my wife said to me, what do you want for your Christmas? And I went, I want an iPad. And she says, no, what do you really want? I went, I want a jumper. Okay? You've all got women like that, yes? Everybody got a woman like that? Yeah? So then she says, okay, for your birthday, what do you want? I says, I want an iPad. I really do. She says, okay, tell me what your Windows phone and your laptop does that an iPad doesn't do. Damn it. But I eventually got one. And now, of course, I want it to be obsolete because I want a Windows tablet thing, which I'm really looking forward to seeing. So, cool. So, have you all seen some good sessions? Yeah? Okay. There's a VB one, actually, just a couple of doors down. So, you know, no, okay. Who's going to the football game? The soccer thing tonight, yes? Okay, I'll buy you a beer. I'm from Scotland. We're generous people. You know what? I might even buy you a hamburger as well. Okay, cool. Well, I guess it's just a minute to go, so I suppose I could start, couldn't we? We could kind of get things on the road. Well, a very good evening. How is everybody? Good? Enjoying the summertime in Amsterdam, yes? Yeah? The best winter I had was a summer in Amsterdam. It's true. It's true. Anyway, for those of you who I haven't met before, shame on you. Good afternoon. My name is Andy Malone. I'm from Scotland, but please don't hold that against me. I'm an MVP in enterprise security for 7 years and also a MCT, Microsoft Certified Trainer, for 17 years. Golly, does it? Wow, it's a long time. Who's been in the game a long time? Anybody remember DOS and Windows, early versions? Wow, you're really old. Okay. Anybody remember the abacus? No, I'm joking. Okay. So, as I say, very good afternoon to you. Welcome along to the Cryptography Chronicles. I'll tell you where this came from. A lot of people say to me, Andy, you keep doing kind of cybercrime stuff, hacking and all of that. And I thought, yeah, I do, don't I? And a lot of people said to me, I don't know much about cryptography. Can you maybe do a session on cryptography? So, I'm listening to you guys and I'm doing a session on cryptography. This is... Although it's over 2 sessions, I put content together and it was just so much to put together. So we basically split it. So this session is kind of all the kind of the theory behind it, the theory and the history and how it's developed and moved on. The second part is all about the modern stuff. We do lots of cool demos in the second session. Guess when it is? Friday, 5 p.m. No, it's not 5 p.m. It's something like 2:45, something like that on Friday. Anyway, it's the last session, so I hope very much that you can come and see part 2, because we've got some cool stuff in there. So this is if you are a beginner in cryptography, it was quite difficult to place this session in terms of kind of techie stuff. So it goes from the very simple to quite complex, okay? But the 2 sessions. So when I say level 400, I'm really talking about the 2 sessions kind of together, okay? So we take it from the basics, the history, the development, and we kind of move up a little bit to, you know, the quite kind of complex as well. So just to give you a little bit of feedback on that. So part 1, as I say, is all about the kind of the basics of cryptography. So it's history, where did it come from? Normally came out of war, to be honest. So war and cryptography are 2 kind of things that kind of go together. There are different types of cryptography. So we're going to look at the different eras. We're going to look at classical cryptography. We're going to look at modern cryptography as well over the next 2 sessions. And also, where would you typically use this? So obviously we use it both physically, data at rest type scenarios, but we're becoming more and more reliant on obviously cryptography in the cloud, or cryptography sending mail, e-commerce and so on. And then I'm going to take some examples of cryptography. There are loads of examples of crypto. Lots of different algorithms that I could look at, but I wanted to take a few kind of what I think to be the kind of key ones. So I'm looking at AES encryption, formerly known as Raindoll, and I'm also going to have a look at Diffie-Hellman as well, who are considered to be, if you will, the grandfathers of kind of public key cryptography. So they're the 2 kind of algorithms I'm kind of going to have a look at. So first, the second session, by the way, this is what we're going to look at in the second session. A lot of cryptographers will think that, hey, you know, my crypto can't be hacked. It's absolutely foolproof. It will never be hacked. And let's face it, history has shown that in time, most cryptographic algorithms have been cracked in one way or another. So we're going to talk about the controversies of it, and I'm going to give you some examples of even very, very good cryptography, how it can be cracked and hacked. We're going to look at data in transit, data at rest solutions. We talk about BitLocker, we talk about TrueCrypt, technologies like that. On Friday we look at public key certificates, we talk about PGP, pretty good privacy. Again, I'm going to take some examples, some specific algorithms, and look at them in more detail. So we're examining SSL in great detail, and we're going to look at IPsec in detail as well. And I'm also going to talk about some of the new and emerging cryptographic algorithms. So we'll talk about, well, I'll leave that till Friday so that you'll hopefully turn up. So a good place to start, of course, is let's start at the beginning. So basically, where did it all start? Well, basically, cryptography is as old as humanity itself. So it can be really kind of dated back to the Roman era, the Greek era, the Egyptian type era. But these are kind of specific dates in history, and you can see it all has to do with communication. So basically, as one kind of media is created, so too the military pick it up. So you can see the radio in 1903, of course, the 1914-18 First World War, and then, of course, the Second World War, Alan Turing, which was the video that I just showed there. 1975, of course, IBM developed the first personal computer, but there they also developed the first cryptographic algorithm there as well. And of course, the mobile phone, and you notice I actually said 1946, because that's when the first mobile phone was actually created. So when we talk about what cryptography actually is, let's break it down from the very beginning. So in essence, cryptography is a form of secret writing. So the ability to hide a message or text into something that is completely unrecognizable to Joe Public. There are multiple different types. So you have something called stenography, which is essentially hiding messages, text within images, pictures. Okay? And the other one, of course, is cryptography. With cryptography, there are, again, two types. So there's substitution ciphers, where you substitute a letter for a number or a letter for a different letter. Okay? Also, the transposition ciphers are typically where you move a letter from, and an example of that, of course, is the Enigma machine. The algorithm itself is the method that you're going to actually encrypt the technology, and of course the cipher is the actual encrypted message itself. The key is everything. So with all cryptography, if we don't secure the key, it's completely worthless. That's the key thing here. So if you don't secure the key, it is kind of worthless. So why do we use cryptography? Well, the number one reason, of course, is authentication. In fact, these are the reasons. So authentication, authorization, privacy, confidentiality, integrity, and non-repudiation. So authorization, you come to a conference like this, you can't get in the conference without your badge. So that shows the security guards here around the RAI that you are authorized to enter the building. But you've all got different colors. So you're green, you can go into certain areas of the conference center. I'm a speaker, I can, for example, go into the speaker room. I'm authorized to do so. Privacy and confidentiality is becoming more and more important. So it's more critical, the more that we share information on the internet, the more information that we store digitally. Privacy is absolutely everything. And of course, if we're putting data out on the internet, we want to ensure the integrity of that data, that it's not been changed or manipulated in any way or form. And ultimately, if you send me a message and I phone you back and say, I'm sorry, I never received your message, then, you want proof of that. So this is where non-repudiation comes in. So these are kind of the main reasons that we use cryptography. And we have a whole series of tools that help us manage these. Okay, so where to use cryptography? So we can use cryptography in military. So typically the military would use this, and I've done a number of projects with both the US, UK, Norwegian and Danish military organizations in terms of this. Defense against external hackers. So, for example, we might secure our routes into our network to stop somebody using something like Wireshark. So if you use tools like Wireshark, you will have real problems trying to get over an IPsec channel, for example. Defense against internal hackers. So obviously we're all concerned about somebody walking up with, let's say, a thumb drive. How do you protect against that? Encryption is the way. Unfortunately, one thing encryption cannot protect against is me just walking up and potentially deleting data. It's not that clever yet. Securing e-commerce is probably the biggest challenge that we have today. So we've seen recent hacks, we've seen LinkedIn, we've seen various banks in the UK, we've seen problems. If services go down, we have real issues with that. And of course, securing financial systems. So when I pay with my credit card, I need to know that it's absolutely secure. And, for an author like J.K. Rowling, she took a long time to put her book, or her Harry Potter books, out in digital format. So when they went out there, she had to be sure that they weren't going to be stolen. So again, the protection of intellectual property rights, and also liability avoidance as well. So non-repudiation is a good example of that. So the next thing we're going to do is, well, before you're going to be a cryptographer, you need to learn to speak like a crypto geek. So plain text, of course, as I said, is the plain text. The key is absolutely everything. So it's the sequence that controls the cryptographic operation and the behavior of the algorithm itself. Then we need to think about, okay, the ciphertext, so the actual encrypted data itself. The cryptographic algorithm that we're going to use, and I'm going to show you a few of these today, the actual key space, so the total number of keys. So, for example, an AES 256 key has a much bigger key space than an AES 192 key, obviously. So the bigger the key space, the less chance of somebody potentially hacking it. The initialization vector. So what a lot of cryptographic algorithms do is they use mathematics, they encrypt the data, and then they throw in something random just to kind of, throw it up there. So generally random, I've got an argument with this, I'll talk about this on Friday. What is random? So we'll speak about that on Friday. Finally, the actual crypto system itself. So the actual sequence, the combination of all of these things together. So this is basically the language that we're going to use. So how did it begin? Where did all this come from? Well, as I've mentioned, cryptography is approximately 2,000 years old. And this is an example of the very first type of cryptographic tool used. This is the Spartan method. So basically Sparta, they had a wooden stick, they tied a leather belt round the stick and basically scrawled in symbols or letters. So the stick had to be exactly the right size, obviously to be able to decode the message. So this was the Skytail method. At Bash, this was a Hebrew cipher, and it was essentially known as a fold cipher. So, for example, I'll give you an example in a second, where you would essentially fold the letters in. Caesar cipher, you can basically move the letters in the alphabet. Let's say you move them by 3 positions. And again, Vigenère uses multiple cipher keys, or multiple ciphers, or multiple alphabets. To avoid repeated characters. So the first of them is the @bash. This is a substitute cipher, and this came from the Hebrew alphabet about 1900 years ago. So a very, very early version, and you can see the way it works. Basically, they've just essentially reversed the alphabet here. So A becomes Z, B becomes Y, and so on. So again, pretty simple, really. Very, very simple example. Probably one of the most famous is this man. This is Julius Caesar. And his cipher was in fact, very, very clever at the time. So essentially, you chose a number, and you basically, I'm going to move the letters along by that number. So 3 in this example. So Microsoft TechEd thus becomes this. So the problems with Caesar's cipher, in fact, most of the problems here is, if you know that it's a simple key space, you could pretty much work out that a pattern attack, you're eventually going to work out the message. So it is potentially vulnerable to what we refer today as a brute force attack. So, by the way, I've got a prize. I will give a prize to the person who works that out. So you want to take a note of that little message, because I'm going to come back to that. Take a little note. And this is going to be a little prize. And it's not 3, by the way. Okay? So, take a quick note of that, and there will be a prize at some point. Okay, now, obviously where this falls down is, what if the alphabet is not English? Because it's essentially based on the English alphabet. Of course, you can use any alphabet. Essentially, it's all pretty much the same thing. So whether you use Swahili, Arabic, Mandarin, whatever, it's pretty very, very similar in concept. There was Bellisio in 1553. He came up with this idea of having multiple Caesar ciphers. And essentially, he had a keyword. So again, he chose that keyword. And you can see that with that, you could potentially have, many, many more potential keys. And essentially, if you've seen movies like the Da Vinci Code, another example is the wheel example with that. But you can see that all of these methods, these pattern methods, were pretty easy to kind of work out. So what we have next is something called a monoalphabetic cipher. This is basically where we randomize things. So rather than just having a pattern, we basically mix things up a little bit. So you can see here, hope you enjoy TechEd, is, you would find it pretty difficult to work that out. So this is that wheel that I just mentioned. So with this many keys, it's now possible to secure the algorithm. So the problem with substitution ciphers, though, as you've worked out, is it's all down to patterns. So once you can see the pattern, once you work out the pattern, it's quite easy. So let me give you an example of that. So essentially, we have a ciphertext word here. So I know, for example, let's say it's a Caesar text. So essentially, we just try it with different numbers, and eventually we will come up with the right answer. So that's the problem with that type of attack. So this was a genuine message from Vietnam, from the Vietnam War in 1971, that was transmitted and received. So when you look at this message, you think, I have no idea what to base this on. But when you look at this message, what are some of the letters that kind of openly jump out at you? Shout them out. O's, yes? Yeah. Any others? Well, for me, I would say it was the Z. The Z kind of popped out at first. But then when you look a little bit, there's an awful lot of Z's. And then when you move closer, there's quite a few W's as well. And you can see, as you look in here, you can see patterns starting to emerge. Okay? So there's, again, you look at a random piece of text, and you see these patterns starting to emerge. So the key thing about the English language, in fact, like many other languages, most Western languages, is that they are all based on frequency analysis attacks, potentially. We all use the same letters. So there's a number of letters that we use all the time. So you can see E-T-R-N-I-O-A-S essentially take the most number of words in the dictionary. So other letters like Z, J, K, and Q, this is why you get high letter scores, obviously in games. So there are tables that exist. You can go onto websites, there are tables of this which help you basically do this type of attack. So again, so once you now know that, you can now do a pattern analysis. And having done that pattern analysis, you can see ZWP works out as the. So when you go back to the message and look at it, it can be pretty easy to determine. Okay, so again, 1971. Okay, so the next thing then is, that's kind of the classical era, as we call it. What about the modern era? Well, as you saw with the little video at the beginning, the Enigma machine really was a game changer. And Germany almost won the war if it hadn't been for men like Alan Turing, who helped decipher the code. So essentially, it was an incredible device, one of the smartest devices in the last 100 years, I would say. So essentially, we had cipher disks, rotors, and a lamp board. So 3 elements. And any one of these elements changed, it would completely mess things up. Now, oh, by the way, if you want to have a go at the Enigma machine, there is a free piece of software that you can get. I'll put a little link on there. Incidentally, at the end of the deck, all the videos, any kind of demos and things that I'm going to show, the links for the video are included in the slides. And you'll be able to get these tomorrow, I believe. Okay. So, again, with the Enigma machine, though, it's all down to the key. So if you know the keys, you know everything. So this was a German code book that was stolen. And you can see what we have here is the book. Every day, the operator would need to put in the date, which rotors to use for that particular day, the ring setting, the plug board setting. So if I didn't have a code book, it was basically impossible to decipher this. So, and it was very clever as well, because every time you entered a key on the keyboard, it would move the rotor by 1 place. So it would make it very, very difficult, again, with no code book, to decipher a message. Brilliant, brilliant invention. So, strong encryption then. So the Enigma machine is a perfect example of strong encryption. So strong encryption is made up of a number of elements. So confusion changes the key value every time it's used. Okay? It's performed through substitution, so it moved the rotors. And also, it complicates the plain text relationship. Diffusion, on the other hand, changes the location of the plain text ciphertext. So it changes it. And it's done through a process of transposition, so moving things. So the Enigma is a perfect example of something that uses strong encryption. Very powerful. So looking for today now, so moving forward, of course, cryptographic algorithms that we have today are pretty well known. So we have something called symmetric key cryptography, typically used for data that doesn't really move very much, so data at rest scenarios. Asymmetric public key encryption, so you use this every time you go shopping on the internet. And of course, hash functions. So hash functions, if you write a piece of code, you want to put a hash value against it. Therefore, if I even change it by one character or one bit changes, the hash function will change. That's the theory behind it anyway. Now, current cryptographic standards, it is growing. It is a huge growing arena. So what we have here is we have encryption on the left there that controls things like privacy, confidentiality. On the right, we can see digital signatures. This allows you to authenticate yourselves. Non-repudiation type services. So with encryption, we have both symmetric and asymmetric keys. So both data at rest solution and a data in transit solution. We have public key at different algorithms there, and you can see the ones I've highlighted in red, the other ones I'm going to talk about here. Then we have message digest as well. So these are our hash algorithms, and I've put in SHA-3 there, by the way. NIST, the North American Standards Institute, are currently engaged in a competition about the next version of SHA, and that's due to be announced in December this year. So that's going to be very exciting. Of course, we also have some key management mechanisms as well. So, we all use Kerberos. So every time we log into Active Directory, we're using Kerberos as a key management system, and so on. Okay, so let's look at the first of these in detail. So this is symmetric key cryptography. So it's a fast solution to encrypt data at rest. So if you're using technologies like a database, you've got a laptop, for example, you want to ensure that your data is absolutely secure. So you would use a crypto like AES encryption, for example. So the benefit of this uses a single key, but very, very fast to encrypt. The downside of this, it is potentially vulnerable to a brute force attack, which I'll talk about later. So examples of this type of crypto include things like TrueCrypt, BitLocker, and there's loads of them basically out there. And I'll give some examples. Now, the problem with this type of cryptography is where do you store the keys and how do you store those keys? So, for example, you need to remember if you're using BitLocker, I need to back up my recovery keys. I also need to back up my certificate as well, EFS as well. The symmetric cipher types. So basically we have both stream ciphers and block ciphers. So block ciphers tend to encrypt blocks of data at a time, whereas stream ciphers only really work on a single bit at a time. So some of the examples then. DES, the Data Encryption Standard, 56-bit, designed by IBM, adopted by the National Security Agency in the US. Now, to be fair, they kind of dumbed it down a little bit. It wasn't originally going to be 56-bit, but they kind of dumbed it down a bit, and they've kind of taken ownership of that. In fact, they've taken ownership of many cryptographic algorithms through the years, but we'll talk about that on Friday. There are some interesting evolutions of DES. So obviously DES was broken. Triple DES, of course, did quite well. But back in 2001, they were looking for something a little bit better, a little bit stronger than DES. So they came up with something called Raindoll, which later was later known. Sorry, let me just hook this back on. There we go. So it was later known as the data encryption standard. Okay, there are a few specific cryptographic algorithms that are commercial. So most of the ones that I've just mentioned are free. But there are a few that are commercially available. So, for example, financial institutions might use these. I'm often asked, Andy, who can write a cryptographic algorithm? Anybody can. What controls are in place to control algorithms? Actually, there are very little in place. Okay? But again, we'll talk about the controversies of cryptography on Friday. So, having a look at AES encryption then. Let's talk about this one. This is quite interesting. So, these two gentlemen, actually from Belgium, were the finalists in the competition to come up with a sequel to the data encryption standard. So, the NIST winner, they came up with a block cipher. It used a variable length. So, we have both a 128, 192, and 256. In many cryptographic tools, it defaults to 128. So in many tools, many free tools that you get, it defaults to 128. So it's probably a good idea to re-look at that. This algorithm was known as FIPS 197. And again, it's now free and available for commercial use. Essentially owned by NIST, who are a public subsidiary of the National Security Agency, but we won't go there, will we? Okay, so to understand AES, you have to think pretty big. So I don't know if you played the lottery recently, but basically you've got a 1 in 2 to the power of 61 odds of winning the lottery and being struck by lightning on the first at the same time. So when you look at the bottom there are 2 to the power of 233 atoms in the galaxy. So 2 to the power of 256, whoa, that's pretty big. That's the number of keys in an AES 256-bit key. That's huge. Okay, so you've got to think big. We're talking big numbers. Next, you've got to think in hex. Okay, so I just put a very little easy table here just to remind you about hex, but I'm sure you all know this anyway. So you've got to think in hex. Okay, so how does AES actually work? Well, essentially, you start with a random number and you basically arrange your data. Your data is converted into what we call a state array table. AES uses a very complex system of 10 rounds with 4 functions. So those 4 functions are subbytes, shift rows, mix columns, and the add round key stage. The final stage is it goes through a key expansion. So the first thing we need to do is we need to see AES in action. So I'm just going to minimize my screen here. So let's have a look at this. Well, here I have a note, okay? In fact, if I look at this note, you can see this is just a text file, okay? So this is just an example of a very, very simple text file. Yet, if I right-click on the note and I choose to encrypt it with AES encrypt, I'll just put a very simple password in. Now, this particular software, some of them don't, but this one creates a copy of it, so you would have to delete the original. So I've got this. Now what I'll do is I'll go back into my hex editor. I'm going to open up the encrypted version of this. And you can see that basically that text message is now unreadable, okay? So the question is now, okay, that's pretty cool, Andy, but how does it work? How does it actually think? Well, I'm glad you asked that question. So, no, I really am. It's okay. Okay, did I mention there's a BB just down the road? No, okay. Okay, so let's have a look at actually how it works then. So let me just flip back to this slide. So my next slide has a little demo. By the way, these are just for me, by the way. I put little things that say click me. But all the animations, the links are in the slide deck at the end. All right? So I'm just going to open up this. So this is basically AES under the hood. So basically the block of data that you're writing essentially takes the first block and it converts it into the state array here. So you can see the state array is essentially 16 boxes, 4 by 4, and then you basically have a random cipher key. We'll talk about how the key is generated a little bit later. But you see there are 10 rounds. Okay, so it goes through a series of 10 rounds. It does a sub-bytes round, it does a shift row, it does a mixed column, and then it does an add round key. So on the 10th round, by the way, it misses out the mixed columns. So if I run this, you can see it just basically fills that in. Now that's it. But you know, if you're like me, you want a little bit more, right? So, I've got to say a big thank you, by the way, to a chap called Enrique Zabala, who gave me this animation, and it's really good. You can, again, you can download this anywhere. So, let's just have a quick look at this. So, this is Raindoll, otherwise known as AES encryption. So, let's have a look at this. So, basically, we have our plain text. The plain text goes through the AES engine, and of course ciphertext comes out the bottom. So let's have a look now at each of these stages in detail. So when you encrypt data in Windows using AES encryption, this is actually what's happening. So this is our state. So this is that state array table, and you can see this is a block of my data. So basically what happens here is it goes through a series of changes. So let's have a look at the encryption process itself. So this is the whole process. So you can see you've got the state table, it adds something called a round key, goes through the sub-bytes, shift rows, mixed columns, and then adds that round key, except on number 9, and it misses out the mixed columns. So you can see this is basically what's happening. So 5, 6, 7, 8, 9, and 10, it misses out the mixed rows. And eventually, we get our text. So let's look at these in detail. So the first one then is the sub-bytes stage. So I mentioned hex, right? So basically, we have our converted data here in hex. So we take the first number. So this is 19, so 1 and 9. Now, basically, the guys, they had something called the byte substitution table. So it takes the 1, which is the row, and it takes the 9, which is the column, and whatever the answer is, it basically replaces it. So it does that for all of them. So that's the first thing. That's the first stage. So stage 2 is the shift rows. So with the shift rows, very simple. The first row doesn't do anything, but the second row, it moves over a byte. The third row moves over 2 bytes, and the fourth row moves over 3 bytes. Easy. So AES stage 3, it does a mixed columns stage. This is quite a complex stage, so it basically goes through a complex mathematical calculation here. So it comes up with this. I must confess, it's beyond me, that one. I really tried. Okay, then it does an add round key stage. So it basically does the round key, and this is basically produced as the key that I'll show you in the next step. So that's in stage 19. So basically we take the first column and it does a XOR function between them. So you can see 04 plus A4 equals A4. And if you want to see a XOR function, the best way to see this is by going into the program calculator here. And so if I do a 04 and add this, and do an A0 And the answer is A4. And you can see there we go. So that's what we call a XOR function, XOR, XOR function. So you can see it does that for all of these. Okay, so that's stage 4, the add round key. So it goes through the various rounds. So 7, 8, 9, misses out on 10, it misses out the mixed columns, and then finally comes out with the output. Okay, what about the key schedule then? So how is the key actually generated? So what we have here, again, is the cipher key. So we take the cipher key, and it does a rot word. So a rot word basically just takes the top, and it just puts it at the bottom. Okay, it then does a sub-bytes, so just like the stage earlier. And then it goes 3 rows back, and it does a XOR function, and also it does an archon function as well. And it does that for the first column. For the second column, it just goes 3 rows back and does a XOR function. And again, and again. Okay, that's the first round. Then the second round is as a rot word, plus the sub-bytes, XOR function, and adds a round constant, and then keeps going. So you can see, it's pretty complex. Okay, so it does that 10 times. Okay, and that is how AES encrypts data. So what looks like a very, very simple, just mixing things up, is actually a very, very complex amount of cryptography going there. Okay. What about asymmetric cryptography then? So I've mentioned that this particular or symmetric cryptography is great for data at rest solutions. So your database files, your hard drive, maybe a thumb drive with technologies like BitLocker to go. Great. What about data on the move? Now this is becoming more and more important. So asymmetric encryption, again, there's a lot of examples of public key cryptography. So digital signatures, the key exchange. So again, we'll talk about this concept of key exchange. Also, secure communications. So technologies like SSL, IPsec, all rely on this. So essentially, what we have, asymmetric cryptography can be classified into 3 things. So encryption and decryption. Okay. It provides secrecy. Digital signatures, of course, provide authentication. And the key exchange of session keys, it requires normally 2 keys here, whereas the symmetric key can only work with 1. Now, the good thing about asymmetric key cryptography is that you have a lot more uses for it. It can potentially be quite useful. However, the downside is it's not particularly good in one single location. Okay. And I'm going to give some really good examples of this in part 2 when we look at digital certificates and so on. Okay, so asymmetric keys, these are, a lot of these are freely available. Okay, publicly available. It scales very well because a single key pair is essentially available. The downside, though, is that many mathematicians are now starting to believe that asymmetric cryptography is approximately 1,000 times less secure than symmetric. So obviously the best solution that you can come up with is the use of both. Okay? So again, examples, RSA, Diffie-Hellman, and so on. These are some common examples that we use kind of every day. Where would we normally see these? Well, every time we shop on the internet, web browsers, SSL, technologies like IPsec. remote networking solutions, such as direct access or remote access services, virtual private networks, digital signatures, all of these would typically use public key cryptography. So let's have a look at some of these in detail. A couple of nice gentlemen here. Diffie-Hellman. These guys are considered to be kind of the grandfathers, if you will, of public key cryptography. So Whitfield Diffie and Martin Hellman. Now, they came up with this idea, Paula and Andy, okay, we'll call them, okay? And the man in the middle, by the way, is going to be our evil friend Marcus, okay? By the way, we're having a security talk tomorrow, Marcus, myself, and Paula. I hope you can make that, by the way. Okay, so let's take a look at Diffie-Hellman. Now, Diffie-Hellman was, again, simple, but really quite brilliant, okay? I've got a funny story to tell you first. A Bedouin tribal leader, this is a true story, by the way, I believe it's true, okay? So, a Bedouin tribal leader comes to visit Europe about 150 years ago. He comes to Europe and he sees this and he thinks, whoa, that's amazing, I got to get one of those. So he takes one back with him, okay? And he hooks it onto his tent. And of course he's a little bit upset that when he turns the tap, nothing happens, okay? So the key thing here is that although we know X is easy to produce, okay? X is very, very easy because X is the tap. We can see what it is, we can see how it works, but Y is very, very difficult to reproduce, okay? Sometimes this is referred to as a one-way function, and this is the brilliance that became Diffie-Hellman. Just going to have a quick drink. So, let's look at some of the maths behind it then. Okay? Keep it simple. I'm going to make it simple. So, oh, sorry, there you go. He's a bit confused. So we want to keep it simple, right? So, first of all then, to understand Diffie-Hellman, to understand the key exchange mechanism, you need to think in mod P. So this is called modular arithmetic. So as soon as that you start at 1 o'clock, it's eventually going to come back to 12. So basically the number minus 1. So this is called mod P. So basically assumes that there are multiple different ways to calculate the result from a different inputs. So you can put multiple inputs in, yet get the same answer out. So, for example, 2 times 3 times 5 is 30, 2 times 15 is 30, 3 times 5 is 15 times 2 is 30. There's multiple different ways to come up with the same result. So that was how Diffie-Hellman thought. So, Paula and Andy are true strangers. Not really, we're quite good friends. And basically we come out with 2 completely separate numbers. But when we calculate these 2 numbers, they form the same shared secret. And the brilliance of Diffie-Hellman was that even if Marcus, or the bad guy, managed to get the shared secret, he could never work out what the personal numbers were. It was impossible. Or so we think, anyway. So modular arithmetic works on this principle. All integers are natural numbers. They basically all map to a set of numbers which essentially range between 0 and n minus 1. Okay? Now, that number n can be anything you want. It can be as big as you want. It can be absolutely ginormous. It doesn't really matter because it goes with the principle all numbers map to 0 plus n minus 1. Okay. So that was the brilliance of it. So this is basically how it works. We select a number. Let's call it n. Now, typically this number is at least 512 bits. Okay? So typically it's a reasonable number. Okay? So we'll call this n. We also select a root. We need a root, or r. Now, there are a few kind of mathematical rules for this, but we'll keep it simple for now. So basically we take r, and we add this with n. So n plus r equals our shared secret. Okay? So again, Paula, she now picks a very large number. I mean, difficult to remember. Very, very large number. This will be Paula's secret key, or A. Okay, we'll call it A. So once selected, Paula then raises r to the power of A. Okay? Once she does that, no matter how big that number is, and you would think, whoa, to the power of that number, that's going to be absolutely enormous. But remember, we're using modular arithmetic here. So no matter what number we're working with, we'll always map between 0 and n minus 1. Okay? And we'll call this x. Okay? X. So, mathematically, there are tools available, and you can get them, you can download them. They allow you to calculate x from A. Okay? So, we can easily get that. And that is the example of the one-way function. Okay? So you get on a plane, or you see all the controls on a plane, and you think, oh my, how on earth does this plane fly? You can see x, but you can't see y, how to actually fly the plane. Okay. So although that is easy, the reverse is very, very difficult. Okay? So A to x is easy, but x to A is impossible. In theory. So we hope, anyway. So, Paula sends me her public key, x. I get x. Okay. Now, again, I would find it very difficult to find A from x. So if I've got Paula's secret key, x, I could never work out what her private key was from that. It would be very, very difficult. If Marcus is in the room, you're not really evil, by the way. Okay, thus giving Andy x preserves A as a secret. That's the key thing here. You see that? So I then do the same thing. I select a secret. I'll call it B. I'll call it B, right? This is my shared secret. And again, I raise B, r to the power of B. We'll call it y. Okay. And I'll give Paula y. I'll say, there you go, you can have y. So that's my public key. So Paula, again, cannot reverse engineer my secret key from her public key. Okay. Interesting. So, Paula has a private key, and she also has my public key. So I've got hers as well. So B plus X. I've got her public key. So Andy's public key is Y. I can now this is the clever stuff. Now that I know her key, what I can now do is raise R to the power of A multiplied by B, the same as 2 times 3 times 5, remember that? Exactly the same idea. Okay? And can she do the same thing? You'll notice there's multiple different ways to do it. So again, it's the same principle. So can I do the same as her? Absolutely, yes. Because we both know what X is. So I now raise x to the power of b, and I get z. She takes r to the power of b and gets y. She does the same thing. So we now can see each other's public keys, thus preserving our private keys. So finally, I calculate the result, z. We now have this shared secret between us. So only A and B know the shared secret. Okay. So even if a third party gets hold of Z, okay, or gets hold of A or B, if he discovers A or B, it's very, very difficult for him to work out what Z is. Now, I thought you might, that's kind of mind-blowing. So what I thought, let's do it in picture format. Okay. We like pictures. Yes, it's too late on a Friday night for mathematics, right? So let's do pictures. So this is the same thing. So Paula has a blue key that she wants to give to me, right? So basically, she's got her private key. She's got her red padlock and her red key. And I've got my yellow padlock and a yellow key. So what she does is she places her key in a chest, in a box. And she locks it with her padlock. Okay? And she sends that over the wire. Okay? Over the wire, comes to me. And you see, Marcus, or the bad guy, can't hack it because it's secure. So, of course, I receive this. I can't open this. But what I do is I take my padlock, attach it, and send it back to Paula. Paula then removes her red padlock, sends it back to me. And, of course, I can now remove the padlock. And the secret is secure. Okay, that is the brilliance of key exchange. And that's essentially how it works. And that's the brilliance of the maths behind Diffie-Hellman. Okay? Now, if you're anything like me, tonight you'll go straight to the nearest coffee shop and smoke a few. Okay. Wouldn't you say so? I would, yes. I need a drink after that. Absolutely. Coke Zero goes a long way, my friends. Okay. So, brilliant. Simple when you think about it, but brilliant how it works. So when we talk about key exchange, that is the process that we use. And also, this concept of a three-way handshake, I suppose that could come from that as well. Another type of cryptographic algorithm tools are hash functions. So we see these all the time. So if you've written a report and you want to ensure that it maintains its integrity, what do? You assign a hash to it as well. So if you make that report available, I merely need to go back, compare the hash values. If they've changed, I know that that data has been manipulated somehow. Okay. So this is, again, perfect example. So you can see here I've got the word fox, and I assign a hash function to that. If I add text, if I make changes, the hash value changes. Now this is particularly useful for people who produce code, developers, and also IT pros and users alike. Okay? So this is the key benefit of this. So basically takes a block of data and returns a fixed size. So the good thing about hash algorithms is that they're very, very fast. Very fast. Okay? But great for data integrity. Great for that. Okay, current hash values. There are some weak ones which should be avoided. So things like some of the ones at the top there, MD5, for example, no longer in use. SHA-1, it's still in use, but it has, in theory, been broken. At the moment, NIST are in the final stages, round 3 of a competition to come up with SHA-3. So the winner of SHA-3 will be announced in December this year. So that's going to be interesting. You can find more information on the NIST website in that. Okay, so if you were to design a hash algorithm, these are some of the things that you've got to potentially watch out for. So we don't want collisions occurring. A collision is basically where you change something and it comes up, you can basically duplicate the result. So you want the hash value to be different every time. So if you get the same hash value, then there's an issue. That's what you want to avoid. Okay, what I thought I would do is just show you just very, very quickly. I showed you the AES tool. I wanted to show you a tool called TrueCrypt as well. I don't know if you're familiar with that. TrueCrypt is, obviously we have tools like BitLocker, drive encryption, absolutely fantastic. It's great if you have a trusted platform module. If you don't have a trusted platform module, it does have some issues, which I will discuss on Friday and show some weaknesses there. TrueCrypt, of course, really, really simple. I'll just create a quick volume here, how it works. I'm going to create an encrypted container. Now, the nice thing about this is you can encrypt a single file, you can encrypt a volume, and you can also encrypt a system volume as well. But the real sneaky thing that this does, you can also encrypt a hidden system volume and install a hidden operating system, which makes it very interesting. Another thing that you can do is you can install a hidden volume within an encrypted volume. And in fact, you can keep going and keep going and keep going. So somewhere in there you can have a virtual machine, which is really quite cool. So if I go for the standard trusted volume, I'm just going to select a file here. I'll just put this on my desktop. I'll just call this Andy. I'm going to call it JPG. Okay, it's a JPEG file, of course. I don't want you to know what it is. Yeah, you can see I can choose my algorithm here that I'm going to go for. Some of these were actually finalists in the AES competition, of course. So I'm just going to go with AES encryption. And you can also choose your hash algorithm here as well. I'm going to go next. Going to create an 8 meg file here. And I'm going to put in a very simple password, password 1. And you can see I can also use a key file. So as well as a password, the file also has to be available as well. So click next. Yes, it's saying I've got an easy password. I'm just going to move my mouse around. And you can see it auto-generates a AES key, which we spoke about already. So the volume is now created. I'm going to cancel that for a second. Okay, so if I go into my machine here, I'm going to open up. Actually, let me just move this out of the way. I've got a JPEG file here. Okay. Oh, look at that. That's the cover of the book I'm writing. Okay. How did that get in there? Okay. Okay, so I'm going to go in and open up a genuine file. So I'm going to go into my hex editor and I'm going to open up. I'm going to go to my desktop and I'm going to say, there's my picture. And you can see, sure enough, this is a genuine. I know this is a genuine file. It's not been changed or manipulated. You can see because every file type has a file signature. The file signature here, of course, is Yoya. So again, I'm going to open up another file, and this one is Andy, and Andy JPG. Yes, okay. Basically, if I was going through an airport with that, right now the cop would have his rubber gloves on. Okay, and I'd be quite afraid. So, But the only problem with that, of course, is that if the police officer says, hey, do you want to... In fact, I'll do the demo. I will just pull this over here. I will mount this volume. Oops. And I will put my password in. Okay, I can just open this up. I can put in a file which says, let's say, good stuff. Okay, close that down, dismount that. But let's make it more interesting very quickly. What I'm going to do is I'm going to go into TrueCrypt again. I'm now going to create another volume, but this time I'm going to create a hidden TrueCrypt volume within it. So open up the original file. And I'm going to open up this one. Yep, asks me for my password, so password 1. So next. Again, I'm going to choose AES. I could choose whatever I wanted here, by the way. I'm going to make it 4 meg here. I'm going to put in password 2. This is called plausible deniability, my friends. Okay? So, format it. Okay, so now I'm going to mount this volume again. So the cop, he has a look at my drive and he says, hang on a minute, you've got a formatted drive here. In fact, no, let me put something interesting in here first. So let me just put this as an example. So new. I'll put in here my dodgy movie collection. In fact, we'll call this my evil movie collection. Work with me. Okay, so I'm going to basically dismount that. Right, so of course, you go through the airport, the guy looks through your drive, and by the way, if you have got an encrypted drive and you don't tell them and you won't open the drive, in many countries, especially the UK actually, it's an automatic 2-year jail sentence. Okay? I have a friend in Cyprus. If George is in the room, you'll know who it is. I said to him, so if you discover somebody's got an encrypted drive, what do you do? He says, oh, we'll just hold him until we get it decrypted. Okay, so the guy gets you over, he puts his rubber gloves on, he says, okay, what's your password? And you go, no problem, officer. I'm an honest man. I don't want to be in trouble at all. So, of course, I open up my drive, and you see, I've got nothing to hide. Yes? So I've got nothing to hide. So that is the power of TrueCrypt. Now, to be honest, one of the things that I do is I also do forensics. Okay, I love forensics. Did any of you see the BitLocker thing that I did last year? Did you see that? Okay. Do you want to see it? Do you want me to show you how I broke BitLocker? Right. Sorry, is there any Microsoft people in the room? Can you leave now? Yeah? Okay. Right, so what I'm going to do is I'm going to go into my... sorry, that's another thing. I'm going to mount a drive. I'm going to attach a VHD. How are we doing for time, by the way? Here we are. Oh, it's the last session. There's nobody around anyway. Okay, I'm going to mount this. And, of course, I don't know the password. Yeah? Oh, it's going to... No, I don't know the password. But basically what I've done is there is a vulnerability, not just in BitLocker, but all data encryption technology. And I'll show you the same, I'll show you a cooler demo actually with TrueCrypt, where I hacked TrueCrypt on Friday. So the problem is, of course, I can't get this guy's data. So there's two ways that I could get the guy's data. I could do a memory dump of his machine, which is quite easy, with a FireWire cable. Or I could take a copy of his hyperfill.sys file. So of course your hyperfill.sys file, and the key thing to remember is your hyperfill.sys file is still there even if you physically switch the machine off. Okay? So I can do the same demo with a hyperfill.sys file or a memory dump file. So for the purpose of this, just to remind you, because I'm going to show you on Friday how this was actually done and all the cool stuff behind this. So what I'm going to do is I'm opening a little product called Passware Forensic. This is it's about £1,000, this software. And this is a forensic tool basically where there is nowhere to hide from this tool. I'm going to take analyze the memory and decrypt a hard drive. And you can see I can do it for File Vault, I can do it for TrueCrypt, Mac volumes, it doesn't really matter. I'll choose TrueCrypt. What I've got here is I've got a memory dump file. Here's one I made earlier. So it's a DD image, direct image, and I've got a memory.bin file as well. So I've got an image of the file, and I've got a memory capture. Just so you know, what I've done is I've taken that, the results of that, and there's a little tool that I've used called Disk VHD Creator, and it basically converts the DD file into a VHD disk. Okay, and that's why I can open it here. I'm going to go next, and now it's going to go off. And what it's doing, because that particular machine, that laptop that I ripped that from, didn't have a trusted platform module, the files, or the keys, are in RAM. So what this is doing, what this attack does, it's doing a pattern match through the RAM. Okay? So it takes about a minute. So this demo is the one I did last year, but I just wanted you to see it because this sets up part 2 of this class. Okay? Bear with me, it's coming. So, cryptography. Are we totally secure? Somebody asked me this today, actually. Do you think with the infrastructure that we have today, do you feel completely secure? Yes? No? Okay. So, yeah, there we go. I've got the key. So I'm going to copy that key. I'm going to go into my volume. And, of course, I don't have the key, but I do. I forgot my password. So I can put in the recovery key from RAM, and I've now got access to the drive. Thank you very much. Okay, so I'm going to show you on Friday really how we did that and how it actually works. Okay, there's some cool demos, there's some cool stuff on Friday, a lot of demos on Friday. This lesson was really all about kind of the practicalities of it. Got some tips for you, by the way. Only store sensitive data that you need to be stored sensitively. Okay? Use strong cryptographic algorithms. So I mentioned BitLocker here, by the way. We've still got a few minutes, we're all right. Let me just close that down. Don't need that. But I do need this. Where are you, where are you, where are you? Ah, here we go. So these are the BitLocker settings in Windows 7. Yes, I got Windows 8 as well, but I love Windows 7. I'm an old-timer. Okay. So you can see here, you can choose where to store the BitLocker recovery information. how users recover BitLocker, choose the encryption method and cipher strength. So this is really important. You see, most AES encryption uses 128-bit by default. Okay? So again, you probably want to use the strongest BitLocker key possible. All right? And again, we're going to talk about this on Friday in a little bit more detail. Okay, so these are kind of just my top 10 tips. Use definitely the strongest algorithm possible. Assume or ensure that random numbers are cryptographically strong. Okay? Only use wide implementations of cryptographic algorithms. It's all very tempting to go off and create your own. It really is. But with doing that, there is no proof that they are sound. Okay? Prefer authenticated encrypted modes. I'll talk about that on Friday as well. Ensure that cryptographic protection remains even if access controls fail. So if somebody steals your laptop, somebody steals your server, at least the data is secure. Okay, you can replace the hardware. Ensure that the secret is protected from only to authorized access. Define a key life cycle. So don't go and create certificates with a 10-year lifespan. That's crazy. You're opening yourself up to trouble. At least a maximum of 3 years, I would say. Store unencrypted keys away from the encrypted data. Okay? There's a classic example of early versions of Windows, Windows 2000. You know EFS, encrypting file system. Okay, they actually put the recovery key in the registry. Okay. Okay, what not to do? Use independent keys, multiple keys preferably, and protect keys in a vault. So the key protection is absolutely everything. Okay. So, you're a geek. Yes, congratulations, you're a geek. You survived. Okay. So, on Friday, the last session on Friday, we're going to have loads of demos. Okay. We're going to talk about the controversies, and there's quite a few, believe it or not. We're going to talk about data in transit as opposed to data at rest solutions. We're going to have a look at the strengths and weaknesses of data at rest as well. And again, I'm going to show you some really quite cool things about the future too. There is a lunchtime session tomorrow, so if anybody is interested in bring your own device, again, we've got a lunchtime session. That's going to be interesting in the theatre tomorrow. Cryptography is on Friday. I've also got a security panel tomorrow with Marcus and Paula. That's always fun. So I hope you can be there for that. There are some resources. This slide, by the way, if you look at the notes page on this slide, it's got all the links to all the videos, the demos, and all of that stuff. If anybody wants any of my funny videos from the beginning, just bring your hard disk up and a few euro, and I give you a good price, okay? I make special price for you, yes? Okay. Also, if you're in Cyprus and you'd like to join myself and Paula, we're hosting the next, the Cybercrime Security Forum. This is we run this in multiple countries. 8th and 9th of November. We have got some really cool stuff. And because it's not Microsoft, we can really say what we think as well. So we got some big hacking sessions. We got some really cool stuff. So again, you got the web links there. Please, if you're interested, come and see us. It'd be great to see you. Okay, TechEd resources. Please eval the session. I really hope you enjoy it. Again, for some of you, it would have been a 400. Some of you, for many of you, it would have been a 300. I know getting the level right was never going to be easy with this particular topic, but I really, really hope you've enjoyed it. Have a great evening. I'm Andy Malone. Thank you so much.